Hi, it's your guy Olumide, and today we'll be talking about a common and crucial data structure that is used in solving real-world technical problems. It is the graph. So, graph is a data structure composed of nodes that are connected by edges. So, it actually consists of two things: nodes, a particular node with its value, and edges that connect it to other nodes. So graphs are used to model relationships where the edge define the relationships. Below now we have the code implementation for the graph class. So whenever you want to implement the graph node, previously we talked about the trie node. We've also talked about the tree node. So this is now the graph node, because graph also is just consisting of nodes that are connected by edges. So whenever I want to initialize a graph or a graph node, we just have to set in some basic attributes that include the value. So value of the node, which means the node's value, and also neighbors, so that represents the connection. So because a node can actually be connected to several other nodes, like in this case, look at this particular node with the value 0 connected to three node 3, node 2, and node 1. So now these three nodes will be contained as the neighbors of the node. So most of the time we use lists to represent the neighbors of a particular node. So now let's talk about certain terminologies that are used when we are trying to speak the language of graph. So we have the adjacent node or neighbors, which are two nodes that are adjacent if there is an edge connecting them. So we can call this node 0 and node 3, we can call them adjacent nodes. We can call node 0 and node 2 adjacent nodes. We can call node 0 and node 1 adjacent node because they are connected by edges. So we also use the terminology degree, which represents the number of edges connected to a node. So the degree of node 0 is 3. Why? Because we have 3 edges. This is the first one, this is the second one, and this is the third one. Don't forget that each edges is used to connect a node with another node. So here are 3 edges for the node 0. So, and therefore the degree of node 0 is 3. Now let's talk about the path, right? The path of a path is a sequence of node connected by edges. So as you can see, this shaded region is a path. It's actually a sequence of nodes connected by edges. So this is from a path from node 3 to node 4. So this is what we call a path. So let's talk about certain attributes of a node now. So we have directed versus undirected graph. So in a directed graph, edges have a direction associated with them. So, and this is just an example of a directed graph whereby there is direction. So you can say that this node 3 is moving is actually pointing toward node 0, and node 0 points toward node 2. Node 0 similarly points toward node 1, and node 1 and node 2 points toward node 4. That's what we call directed. So the reverse, or the reciprocate, which is undirected, actually means a graph that is not directed. Also, we have weight versus unweight graph. In a weight graph, edges have a weight attribute associated with them, such as distance or cost. So this is what we call a weight graph here. So you see that this graph actually have some parameters associated with them, like a weight, like a cost, like distance, like speed, or any other factors. We also have the cyclic versus acyclic. A cyclic graph actually contains at least one cycle, which is a path that starts and ends at the same node. So, and this is what we call cyclic graph in the visual here. So it's actually a cycle, is a graph that have at least a cycle, that is it begins and ends at the same node. Look at here now, we see that from node 2 it moves to node 3, from node 0 it moves to node 2, and from node 2 it moves to node 3 back to node 0. So that within these three, this triangle right here, a cycle is formed in the graph. So if there exists at least a cycle in the graph, then it's a cyclic graph. So these are attributes of the graph. Now for representing a graph, we used to represent the neighbors of a graph. Don't forget, neighbors is one crucial property of a graph, or of each node in a graph. So each node will have a value, just like this node have value 0, and it will have neighbors. So to represent neighbors now, we used to use adjacency list, which is actually a list of the neighbors. So look at now, for the particular node 0, it has neighbor as 1, 2 and 3 are its neighbor. For node 1 has only one neighbor, which is actually node 0, and node 2 have two neighbors, which are node 3 neighbors, which are node 0, node 3 and node 4. Node 3 has two neighbors, which are node 0 here and node 2 here, while node 4 have only one neighbor, which is node 2. So that's what we call neighbors of nodes in a graph. Now, for traversing a graph, or let me say for traversing a graph data structure, there are basically two techniques that we use, which is the depth first search method, and the breadth first search method. If you've watched my previous videos, you'll be familiar with these two methods, the depth first and the breadth first. So the depth first is typically implemented recursively. So, and this is how it is being demonstrated. So actually, whenever we call the depth first, so it's actually treated recursively, meaning that we keep calling that method or that function on and on until we get and reach each and every node in the graph, right? So that's what it means to implement the function recursively. We keep calling the function for each and every node in the graph data structure, and what we want to do at each call is that first of all we add that particular node to the visited. We are going to be having a visited set, something like a hash set that will help us to keep track of visited graph nodes. So we are going to add it to the visited hash set. Then we are going to process the current node, right? After processing the current node, then we are going to iterate through the current node's neighbor, and we're going to try to ensure that if that node is not visited, then we want to call this function on it again, right? So simple. Just for each node, we are going to add it to the visited so that we won't revisit it. We are going to process such a node, then iterate through the node's neighbors, and we're trying to check. We're going to check if each of these neighbors are not visited. If they are not, then we will call the function recursively on them. So the BFS is typically implemented iteratively, as demonstrated in this particular code snippet now. So same thing for the DFS. What we do is that we create a set that we're gonna give the name visited. So it's gonna help us to keep track of visited nodes. So we're gonna use a queue. That's why you say iteratively, because we'll be using like something like a queue, a data structure that we can iterate through, right? So using this queue now, we are gonna set in the node that we pass in, which is the root node. So because here we are not going to have to call BFS recursively, so we most likely are just gonna pass in a single root node into the function. So and that root node is what we are gonna pass into the queue as well, right? So now why queue? While there are still nodes in the queue, what we want to do is I want to pop the leftmost node. That's why we are using a queue. First in, first out, right? Yeah. So that's why we are popping left out of the queue so that it can get the first one out. So now we got the node now, and we save it as a node variable. And now we said that if node is not visited, right, we want to add such a node to the visited sets, because now we are visiting it. Then we are going to process such a node. We are going to iterate through its neighbors and append it into the node again, into the queue again. So and we just keep doing that until there is no more node to process, that is until every node has been visited. So this is how we typically solve this one using the BFS method. So now the real world example is in social network. So we really use graph in social network, whereby users of social media sites like LinkedIn are typically represented as nodes. So typically we are represented as nodes in these social media platforms. So and then connections or friendship between a user and another user or several users are represented as edges. So the graph structure allows platform to analyze relationship, suggest new connections, and identify groups or community within their networks. So that's a real world application in different social media platforms, including LinkedIn, Facebook, and other platforms, right? So now we will really be considering problems that are graph related, and I don't want you to miss it, and you don't want to miss it either. So do well to like, comment, subscribe to my YouTube channel, and we will be meeting in the next video.